Hello everyone, welcome back to Project Pro YouTube channel. This is me Simran Anand, and in this video I'm going to be discussing about a topic which is key to building machine learning and deep learning neural networks effectively. The topic is hyperparameter tuning. So in this video I'm going to be explaining you the concept behind hyperparameter tuning, the various implications and advantages of tuning hyperparameters that can significantly increase or decrease the model's performance. Then I'll be later in this video I'm going to be demonstrating the Python program to build a deep neural network, and we'll be tweaking in the hyperparameters to infer various observations by doing the same. So let's begin. So basically, if you know, in deep learning and machine learning models, when you're building, there are different set of hyperparameters, which are nothing but a set of parameters which actually control the performance of machine learning or deep learning models. So say that you're building a deep learning neural network. What exactly do you think could be the hyperparameters which would actually affect the performance of a deep neural network? So deep neural network, firstly, is a combination of various MLP, we can say, or we can say that it's a combination of various multi-layer perceptrons. So multi-layer perceptrons are stacked sigmoid neurons network, but whereas deep neural networks, they consist of the input layer, various number of hidden layers in between, and finally the output layer. That is basically this combination of networks layers is called as a deep neural network. So in deep neural network, there are different hyperparameters which actually affect the performance of a model. And when I say the performance of a model, it's not always the accuracy, but it could be the other metrics of evaluation as well, say precision, recall, F1 score, and so on. So the major hyperparameters which I'll be demonstrating in this example, which I'll be changing, is examples like the learning rate, the number of epochs or the iterations, the gradient descent, the activation function, and I'll be using two sample data sets in my project to demonstrate. So there is a L2D1 data set, as you can see on my screen. This is a smaller data set for demonstration purpose, and this is a sample larger data set which is named as L2D2. We are going to observe the effect of tuning hyperparameters and then applying this exactly the same model on these two data. So basically to demonstrate whether the accuracy of the model will increase or decrease if the data is increased or decreased, or how exactly will changing the hyperparameters like the learning rate, the decay rate, and also changing the or introducing a concept like dropout will impact the deep learning neural networks performance. So before delving into this demonstration, firstly, there is a project which is Learn Hyperparameter Tuning for Neural Networks with PyTorch. You can have a look over here at the Project Pro's website, which will actually give you the idea behind what is data preprocessing and some of the hyperparameter tuning examples. So say you should be aware of the concept of overfitting and underfitting. So in any deep neural network, various models are very prone to especially the deep learning models are prone to overfitting problems. And why is that so? It's because when your model is actually giving a very good training accuracy but fails on giving a test accuracy, or is not able to generalize well on the test data or the unseen data, that is where overfitting problems comes into picture. So to just name a few, some of the regularization techniques which you can take the hyperparameter tuning which you can apply in order to overcome overfitting problems are data augmentation, like I have already mentioned in my previous videos. Other than data augmentation, you could try out dropout, regularization, and early stopping checkpoints, the changing the learning rates, and so on. So basically, when I say that if your data set is imbalanced, that is the number of minority classes and majority classes differ. Basically the number of the proportion of the classes, the minority and the majority classes differ in value. So that is an imbalanced data set where there is no balance maintained in the different values assigned to the different the classes. Basically, there's a improportionate number of classes present in an imbalanced data set. So even for countering problems in such imbalanced data set cases, you need to be aware of hyperparameter tuning and how exactly it's done. So like I've said, you can also try out dropout. So dropout is basically like when you're dropping or basically removing the connections and the edges between the different nodes present in a deep neural network, and that would actually have a significant impact on the model's performance. So this is a project which will help you understand what are the different hyperparameters, something about feature extraction in order to overcome overfitting problems, and the language used is Python over here. Some of the tech stacks like pandas, PyTorch, Matplotlib have also been enlisted here, and the approach has been followed. So you can have a look over here. in this Project Pro website. Other than this, you could also have a look at recipes tag, since Project Pro gives end-to-end recipes, end-to-end project solutions along with code recipes. If you can have recipes tag hyperparameter tuning, like not only with gradient descent, but then approaches like randomized search, random search in Python, randomized grid search methods can also be used together for hyperparameter tuning, especially in solving machine learning models and problems. So coming to this concept of hyperparameter tuning in deep learning in today's video, let me give you firstly, do you think that deep learning can actually be performed on unstructured data, or can it be unstructured data is basically data which is like examples could be images, video. But when we talk about structured data set, do you actually think we can apply deep learning models to unstructured data set? To structured data set? Well, yes, the answer is yes. You could apply deep learning on structured data sets. So structured data set is in the form of tables. So if you see over here, I have like features. There are 9 columns basically. The last column is the output column or the target column. So the reason why it's called the output label or the target label is because it's already having only it's having binary outputs which are either 1 or 0. So you can think this as a classification problem. So we have a classification problem at hand, which is binary classification. So we're going to look into how other hyperparameters we can set in for performing such classification problem, given that we have a smaller data set and also a larger data set. Larger data set having like around 60 columns or 60 features and more number of rows. So for this, I have made use of Keras models, which can be of type sequential and functional. So similarly, Python, like if you have Keras, DL models can also be implemented using frameworks like, with TensorFlow, PyTorch, or Keras. And it consists of input hidden in the output layer. So with this, skimming through this code, you can see that I have imported the Keras models, which is sequential model to be built, and the dense models, since it has dense layers. So seed, I have set the value to 7 over here. And the reason why I have then loaded the data set, which is L2D1. So the reason why I have set a random seed value to 7 is that whenever you are actually executing the program again, you want exactly the same kind of the train and the test data should be available at every time. So that is the reason you're setting a value, so that there is no random shuffling taking place. The pseudo random generator will be set to the value of 7. That's why it need not be 7, but the seed value can be tuned again. So you could change the value and check for yourself how will be the which one is the best one. So we are going to build in this video, we are going to build a deep neural network having 8 neurons in the input layer. Given that I have shown you the data set, which is L1D1, we can take n neurons in the input layer, 12 neurons in the first hidden layer, and 8 neurons in the second hidden layer, and 1 in the output layer, because it's a binary classification problem. So after splitting the data set, slicing it, and having x and y as the variables, then we can build a sequential model, which is built from using the Keras library. So now that we have built, we are adding in the input layer, the hidden second in the input layer, the first hidden layer, second hidden layer, and output layer. For now, I have just limited the number of hidden layers. Now you should remember that the set of hyperparameters need not be just learning rate or epochs, but or dropout, but rather it can also be the number of hidden layers, which will actually impact the performance of your model. So increasing the number of hidden layers, given that you have small data set, might impact the performance. So in this, by doing this experimentation, you'll come to understand how changing and tweaking hyperparameters, like changing the number of hidden layers and the number of neurons, or even changing and updating weights and biases, will actually impact the model's performance. So there are different automated platforms and tools as well, like weights and biases, MLflow being one of them, which you can which you can make use of in order to perform experimentation tracking, model versioning, and also also track your hyperparameter tuning. So coming to the part where we have added the different layers to our model, we added the kernel initializer to uniform, because uniform initialization, it follows the normal distribution of weights. Activation function used in the second hidden layer is ReLU, which is rectified linear unit. Then there are different activation functions. The sole purpose of activation function gradient descent is also a hyperparameter. So you can definitely check for yourself which activation function performs better. But digging into the deep learning theory, I would say that having a knowledge of which one will actually give us a better accuracy is important. Activation functions, the sole purpose of that is to introduce non-linearity in the data. Given that we have a binary classification problem with labels as only 1 and 0 in the output label, we can take activation function in the output layer can be set to sigmoid activation function. If our data set was, if our problem at hand would be multi-classification, then instead of sigmoid, you could also go for softmax activation function. Then for the second hidden layer, we have used rectified linear unit because it solves the problem of vanishing gradient descent. Now, when I was saying gradient descent is basically a iterative first order optimization algorithm, because it the main goal of gradient descent is to optimize the loss function. We have something called as a loss function and the cost function. Loss function is on the data point, a single data point, whereas a cost function is on an entire training sample. So the goal of the gradient descent should always be to optimize the loss function so that the model's accuracy is increasing. And for doing that, it relies on the backpropagation approach. Backpropagation is a very important technique in deep learning and machine learning models, because it keeps on updating the weights until the most suitable kind of weights is given to the model. It keeps updating the weight so that the model's loss function is optimized and a global minima is reached. So now that we have compiled the model, we have added the loss we have used is binary cross entropy. There are two types of loss functions: the cross entropy loss function and squared error loss function. Squared error loss function works well for regression problems. So since our problem at hand is classification, we are making use of the binary cross entropy, and it penalizes well on misclassification. So that is why we made use of binary cross entropy. Then I have set the epochs or the learning, basically the iterations, the number of iterations, epochs, the cycles of training our model to 150. This is again a hyperparameter which you can change it for yourself and see how it will impact the performance of the model. Batch size I have set to 10. Which means that after every 10 rows, the epoch and as well the learning rate and as well as the optimizer will keep on changing. So batch size is 10. That is for every 10 rows this will happen. So epochs is set to 150. You should always remember that epoch and the learning rate are inversely proportional to each other. And dk, which is the formula, which is nothing but the number of epochs divided by the learning rate divided by the number of epochs, that is dk. So that is again a hyperparameter. Delving into this problem, we have now that we have configured the model, we have fitted. Now comes the evaluate method, which is used for testing the model with the data. Testing the model, we see that the model has given us this accuracy, which is 0.78, 78% around accuracy, and the loss is 0.45. Not bad. We can train a model, change the hyperparameters, and see for ourselves how it will actually impact the model's performance. Now, if you come to see what I have actually changed over here is that I've compiled the model, loss is binary cross entropy. I have loaded L2D1 again. Delimiter is the separator, which is comma. Finally, if batch size is set to 10 here, implies that for every 10 rows, optimizer and initializations are iterated. Again, checking and evaluating the models and checking the score of the model. So you will see that the model's accuracy is 71%. Say this is for your first data set. But now coming to a tactic which is called as k-fold cross-validation. You should understand that k-fold cross-validation is again a strategy or an approach which many deep learning practitioners take in, and it's recommended in order to basically overcome overfitting problems. Again, it's performed on the data. It splits the data into k folds or k subsets, wherein k minus 1 subsets are for training purpose, and the last subset of your data which is split is for the test data set or for the testing purpose. Then after performing k-fold cross validation, you will observe I've said followed exactly the same steps which I had explained in the previous cell, where I have set the seed to 7. Seed implies the initialization state of a pseudo random number generator, so that the same pattern of results is achieved in the model. We get the same kind of results every time this cell is executed. So this leads to less ambiguity in the results. You will create the model. I've defined a function over here, built a sequential model, added the input dimensions to 8. Kernel initializer is set to uniform. Activation functions like ReLU for the hidden layers, and for the output layer, I have used sigmoid activation function. The model is compiled, and then I have split the model with 33% as test size and the remaining as a training data set. Then I have made use of stratified k-fold. Now, stratification is again a statistical machine learning approach, I would say, which is to ensure that each fold, now that you have k folds in your data set, you have split your data set to k folds or k subsets. In each fold of the data has the same proportion of observation with a given label. That is usually for a small data set. Now that I have used L2D1, which is a smaller data set, if you remember, so I have made use of Keras classifier I have passed in the parameters, which is create model parameter, followed by epoch set to 15. Now epochs I have changed again. Previously it was set to 150, but I have changed the epoch number to 15. I have tuned the hyperparameter to see the impact. Batch size is set to 10, and I have applied k-fold cross validation. After applying k-fold cross validation, this is what I achieved. So let me scroll down to the final output. That is after 15 epochs, what will be the exactly the result. You will see that the model has now given an accuracy of around 0.66 with a loss of 0.5964. Now coming to the next case where this is the training phase. Now coming to the first question of ours, which is to infer whether in given this Keras classifier of ours, how will be the exactly the impact of increasing the amount of data using a different data set. So say that I have made a new data set now, L2D2, which is the larger data set. Using the same Keras classifier which I have trained above in the previous cells, what if I use that for a larger data set? Now, increasing the data can have implications. If the data has more noisy, it will definitely decrease the accuracy of the model. But if the data is increased, then I would say that better is the model's accuracy, because more is the data set. For a larger data, the model performs better. So on increasing the data, or by using again a different data set and training a model on the using the Keras classifier, I exactly replicated the code, which is create model, made use of the same hyperparameters like activation functions, the same binary cross entropy has been used. Then I have label encoded. I have imported something called as a label encoder over here, because if you have a look at the larger data set, you will observe that everything is in the form of real values. There is no binary value present over here. So I need to apply a label encoding in order to label encode or convert the last column having characters R and M to numeric values. If you see the larger data set over here, then I will just skim through it. The larger data set, the last column, if you see the B1, it has just R and M as the values. So R and M are not recognized by the machine, because the machine learning model will only understand 0 and 1. So in order to label, encode, or convert the categories, the R and M to labels like 0 and 1, you need to perform strategies like label encoding. So this is the code for label encoding, which is taken from sklearn library. From sklearn, import preprocessing dot label encoder assigned to label encoder. Now that the output column, I have split the data set into input X and the output Y variables. The Y variables over here is label encoded. So now that it is label encoded, R is given a value of 0 and M the value of 1, or vice versa. Now that it is done, I have label encoded DNA model using Keras classifier. I'm actually training our model using techniques which I have just explained you in the previous cell. I have applied stratified k-fold, which is stratification on the after dividing the data set into k different folds. I'm applying stratification to ensure that the proportion of the observations of the given model, the given label, remains the same. So once this is done, let us go to the results and our main come to the main observation of ours, that actually tweaking and changing just the data set, but exactly using the same approach. There is the same Keras model but a different data set which is larger in size. What will be the impact? You will see that the data set is using the Keras classifier on the bigger data set. The data is we have achieved accuracy of 75%. Remember that in the previous cell, okay, there is more over here, by the way. If I just go down to the final accuracy, you will be able to observe the performance of the model. So let me just skim through till the end, so that the final accuracy. So if you see, the final accuracy is around 76.9% or 77%, which is pretty good. So we see that a model has performed way better than the previous model, which was actually trained on a smaller data set. So one conclusion you can draw is that for in our case, especially increasing the data by using, if you have the same model already built, the Keras classifier which we used, if you're performing the classification task for a larger data set and the data is clean because you've already applied the pre-processing technique, label encoded, and you have a larger data set, increasing the data has increased the accuracy. It has given a higher accuracy in our case. So now that you have understood this impact, let us go to the second observation, to second experiment of ours to check whether accuracy will improve with the larger network. Now we have a larger network, not the larger data, but we are using the same data set but a larger network. Now a larger network can be complex because increasing the number of layers will actually lead to more complexity. Now, this model will be prone to overfitting is what is the theoretical understanding of ours. Let us by experimentation see what will be the observation. Now, I have created the same model, increase the layers. If you see, I have this model 2.add every time. Instead of just having 2 or 3 hidden layers, the number of hidden layers have been increased. All the hidden layers have been given activation function of ReLU has been applied. Whereas in the output, I have applied the sigmoid activation function for the output layer. I have used binary cross entropy, Adam as my optimizer. Now, optimizer is one thing you can take a look into. So there are different types of gradient descents and optimizers. Adam optimizer, another one being the SGD or the stochastic gradient descent. And not only these, but you have the momentum gradient descent, then RMS prop, and so on. I've used the Adam optimizer. And let us check matrix's accuracy, that is evaluating the model's performance or by taking the metric as accuracy. By understanding this and splitting the model, I've applied shuffling over here. Random shuffling is set, random state is set to the seed value. Seed value, as mentioned, I have just given a random seed value to 7. And then number of splits, shuffle is set to true. So k-fold over here is a cross validation that divides the data set into k-folds. I have divided the data set to 10 splits over here. And I also applied stratification so that the proportion of class labels remains the same in each fold. Once this is done, and let us see, by just changing the number of layers, by increasing the number of layers and by a larger network, what will happen? We have observed over here that the accuracy is less. So the accuracy has decreased compared to the previous network. This implies that, as you can see on my screen over here, you will observe that increasing it has caused the model to become more complex. So as was in theoretical understanding that it will lead to overfitting, that was observed over here, because it's true that for certain reasons, more the number of hidden layers, especially for the smaller network, more the number of hidden layers, more will be the better training for the model, because it's able to actually capture the inner representations and understanding. But then for a larger network, we're actually increasing the number of layers in the increasing the number of edges and layers, neurons in the network. It will actually lead to a less accuracy because more complexity is increased. The model becomes complex, although it's giving a good training accuracy, but the model fails to generalize on the test data. So if you take the accuracy, which is the validation accuracy or the test accuracy, is just 52.2% in contrast to the previous accuracy of 75%. So that is how drastically the model has decreased its accuracy or the performance. Coming to the next observation, which is checking whether accuracy will improve after dropout or not. As I've explained you what dropout is already, is just a technique of randomly selecting neurons, in which randomly selected neurons are ignored during training. So we can say that dropout is simply like removing the unwanted edges, or just randomly dropping the weights and the edges, removing the connections between the edges. So after performing dropout, I have applied a dropout over here in this model. After we have built the model, and then I have applied dropout over here, the activation functions accuracy optimizer is exactly the same. And on doing this, and you will observe that I have given epochs over here is set to 15. Model x, y, y, and the x train, y train is passed as parameters to the cross-val score to get the training the model and evaluating it on the score. Then I have applied cross-validation as k-fold cross-validation over here. Then you will observe that the mean accuracy has actually dropped after dropout. It's actually increased. Instead of dropping, it has actually increased. So applying dropout is actually having a positive impact on our neural network, because it has actually improved the performance model. So this can be termed as a technique of overcoming the overfitting problem, because it makes the network less sensitive to the specific weights of neurons. So that is exactly the reason, as you can see over here, that why exactly a model performed better and has improved the accuracy compared to the previous model. Coming to the last observation, which is checking whether the accuracy will improve with the decay learning rate, different learning rate, and SGD optimizer. As I've already explained you, Adam optimizer, which is a combination, it's generally thought to be better optimizer, and it's used in most of the projects because it's a combination of RMS prop and momentum gradient descent. That is in the deep learning context. But what do you say that if you directly randomly just changing the optimizers will actually impact your model performance or not? In some cases it does, but in most of the cases, like in our case, if you see that I've just changed the SGD optimizer, which is stochastic gradient descent, it has actually it has actually changed the accuracy. But do you know that how exactly it has changed the accuracy? Although I have applied a dropout of 0.2 over here, that's 0.2 is the dropout value, which is again a hyperparameter, can be changed. I've applied over here added the model. I've built the model, compiled it, but instead of Adam, I'm using SGD optimizer with a learning rate of 0.1. Now, learning rate is 0.1. It is a correct learning rate. So, decay rate have also been changed over here to 0.1 by 15. So decay is nothing but the number of is nothing but the learning rate divided by the number of epochs. So if I say by 15, 15 is the number of epochs which we have built in the model, then used in the model, and then 0.1 is the learning rate. Learning rate initially has to be set to a smaller value, I would say. You could set it to 0.1 or 0.001 or 0.01 as the initial starting learning rate for your model to train on. And this is experimentally proven value. Of course, you can actually empirically change these values and compare the performance of models. Momentum is set to 0.9. I've used SGD, which is stochastic gradient descent. On changing these optimizer and using exactly the other parameters are exactly kept the same, which is binary cross entropy and matrix accuracy. Test size is also same, which is 33% is used for testing. And I have applied Keras classifier over here. Cross validation has been applied along with stratification. Upon doing this, that is by using a decay rate, by introducing a decay rate and SGD optimizer, you will observe that the accuracy of the model is 0.50. Okay, this is the initial one. Let me go to the last, to the end of our training to check that after training for 15 epochs, what has been the impact. You will observe that the accuracy is just 57.14%, which is very less compared to the previous model's accuracy when we were actually using Adam. So this can we can conclude in this way that for our model, especially in this deep neural network, SGD optimizer gave 65.38%, which is less than the one which was obtained using Adam optimizer. So we can say that the reason behind this is that SGD, which is stochastic gradient descent, it actually changes. It actually uses the. It does not change, but it actually uses the same learning rate. So it maintains a single learning rate for all the weight updates, and the learning rate does not change during training. But on the other hand, Adam, which is actually a combination of MGD, which is momentum gradient descent, and RMS prop, it serves better because it actually it uses adaptive gradient optimization and performs a decent number of weight updates. So each time, say weight updation is some concept which is very key to improving the weights as well. Always the weight has to be initialized to something non-repetitive, and the weights of each neurons, weights of each layer you are using should be always less, initialized to something lesser value, and also has to be non-repetitive in nature. So that is something concept which you can use. But then if you have especially when you're training a model using gradient descent, you're just randomly initialize the weights, and your model will keep on iterating. And the gradient descent is an optimization algorithm which will actually apply the objective function, which in our case is the loss function. The goal should always be to find the global minima of the loss function. So in order to minimize or reduce the value of the loss function, your gradient, the back propagation is going to be applied, where the weights are going to be updated in each iteration or in each epoch. So changing the weight is one key. So over here in Adam optimizer, it actually adapts the gradient optimization and performs a decent number of weight updates. But on the other hand, SGD uses a single learning rate. So using a single learning rate for all the weight updates, and the not changing the learning rate will actually lead to a drop in the accuracies, what we have observed in our model's performance. So thus we can say that in terms of stability, Adam performs better, and Adam is more stable than SGD optimizer due to adaptive learning rate and better performance outcomes and metrics. That was all about hyperparameter tuning. And there, in case of underfitting problems, you can also look into regularization techniques. So there are two types of regularization, L1 and L2 regularization. You can have a look into that, and that is also one of the ways in which you can actually improvise the performance of your model, because at the end we just want to build a model which will actually perform the task at hand. In our case, it's classification, by giving a very good accuracy or giving a good metric of ours. So I hope I have given understanding of hyperparameter tuning. You can have a look at the Project Pro website. Do check out the Project Pro channel as well, because Project Pro offers end-to-end project solutions, code recipes, and do buy the subscription plan of Project Pro to avail access to 250 plus solved end-to-end projects. All these projects have been developed by top industry experts working in the top global tech companies. Stay tuned to the Project Pro YouTube channel. Thank you.